In this next chapter, we're going to look at additional aspects of aqueous equilibria, and the first effect we're going to discuss is called the common ion effect. And the common ion effect is a direct application of Le Chatelier's principle. So if we took something like acetic acid, and we're in an aqueous solution, the acetic acid is going to be in equilibrium with H3O plus C2H3O2 minus, or the acetate ion. When the acetate ion is added, the equilibrium will shift to the left and repress the ionization of the weak acid. So this is exactly what Le Chatelier says. So if we're adding acetate ion, we are taking this ion and we're increasing its concentration. When we increase this concentration, the equilibrium shifts over to the left, and we're not going to ionize quite as fully here. This is known as the common ion effect, and we can look at an example based upon this. So what is the pH of a 0.085 molar HNO2 solution, and this solution has a Ka equal to 4.5 times 10 to the minus 4, when 0.10 molar NaNO2 is added? So if we look at this, we can think about what the effect is of adding NaNO2 to an aqueous solution. It's going to be a salt, so it's going to dissolve into Na plus NO2 minus. Here we have a 0.10 molar solution, so we're going to get 0.10 molar Na plus and 0.10 molar NO2 minus. Here our equilibrium that we're looking at now is going to be HNO2 in equilibrium with H plus in solution plus NO2 minus. Now when we look at an ice table, our concentration of NO2 minus is going to be 0.10, and if we're looking at a 0.085 molar HNO2 solution, we're also starting with 0.085 HNO2. Initially, we don't have any H plus present. As the equilibrium proceeds, the change in concentration of the HNO2 is going to be minus X, the H plus X, and the NO2 minus plus X. This gives equilibrium concentrations of 0.085 minus X, X, and X. If we set up our Ka expression, which is going to be 4.5 times 10 to the minus 4, that's going to equal the concentration of X, and sorry, the concentration of our NO2 minus at equilibrium is going to be 0.10 plus X. So our Ka expression is going to be X times 0.10 plus X divided by 0.085 minus X. So if we rearrange this particular expression and use the quadratic equation, we end up solving for X, and that's going to equal 0.000379, and that's going to equal the concentration of H plus. If we take the negative log of that and solve for the pH, we get 3.42 for our pH. Okay, so the common ion effect introduces an initial concentration of one of our products, in this case NO2 minus. Okay, so we set up the same equilibrium expressions. We solve for X, which in this case is the equilibrium concentration of H plus, which allows us to calculate the pH for the negative log of that. And here our pH value for this problem is 3.42. We can do the same thing with weak bases. They'll behave the same way. And any type of equilibrium we look at, we can look into the common ion effect, which in this case allows us to calculate pH, which can be derived from equilibrium concentrations of the various species in a particular equilibrium expression.